In the last video segment of today's lecture, we are looking at how external forces are influencing the dynamics equations of motion. Now, what we're looking at is a number of external forces indicated by Fj. So this is a magnitude and a direction, and we have a number of them that are acting on our multibody system. Now, what we need to do is we have to transform this F, which live in task space, for example, in a world fixed frame, into joint space, into our actuator space. And that happens through this Jacobi transposed mapping, as we have seen earlier. So if given a force in task space, I can pre-multiply it with the Jacobi transposed, and I end up with a torque which is in joint space. So this directly acts on our Q's. And we have to do this, of course, for all the external forces that we have in our system. And exactly the same way, we can also deal with external torques indicated with T here. For the external torques, instead of the position Jacobian, of course, we need the rotational Jacobian because torques act in rotational direction, but we can then map torques, external torques, through the Jacobi transposed, the rotational Jacobi transposed, again into generalized joint space. And there, of course, these taus, whether they're coming from forces or from torques, they have the same dimension, they act in the same generalized direction, they can just simply add it up. Now the last element which I want to very specifically address here is actuator torques, because an actuator typically, let me draw here a small robot arm, so I have link 1 and I have link 2. Now my actuator typically sits on this joint, which means the actuator produces a torque here and the counter torque here. Or it can also be a linear actuator. I draw this here in green, so I have a cylinder here, which produces a force here and a force there. So we are seeing both the action as well as the reaction force somewhere on our multibody dynamic system. So that means what we're typically doing is we are taking the Jacobian of that point and the Jacobian of this point. So we have this one here, the Jacobian of this point, and that Jacobian of that point times this force. And one is negative and the other one is positive. So we have the action and the reaction. And the same happens for torque. So we have the rotational Jacobian of that body and the rotational Jacobian of this body multiplied with this torque that the motor produces. So we have the action and the reaction part in our dynamics equation of motion. And of course you have to pay attention in whether you're taking the right positive or negative sign for both of them. Now let's have a look at this with a simple example. We're going to look again at the card pole setup that we had already discussed previously, and where we looked at the 3 different methods in order to generate the dynamics equations of motion. They all result in the same 2-dimensional equation of motion. However, so far we looked at this setup to be completely unactuated. Now what we do here is we're introducing here a motor. So this is now a motor, which means that this motor can produce an actuation torque, tau A, and this actuation torque produces a torque, Tp, acting on the pendulum, and it creates a reaction torque, Tc, acting on the card, which is minus Ta. Now remember, if we give you an external torque and you want to figure out how this external torque influences the dynamics equations of motion up here, what we have to do is we have to find the rotational Jacobian, because that's how the mapping works. Now rotational Jacobians are given, so my Jr is nothing else than my d omega after dq dot. So I take my angular velocity and do the partial derivative of this angular velocity with respect to my q dots. for a planar problem, of course. Now my Q in our setup is X and phi. So what I have to figure out is what is omega of the cart and what is omega of the pendulum. And omega of the cart is 0, so this cart is never rotating. However, the omega of the pendulum is phi dot. So if I take d phi dot and do the partial derivative of d phi dot with respect to dq dot, I end up with this first rotational Jacobian. If I do the same thing for 0, of course I get like a 0, 0 matrix. So in other words, I have now directly the mapping between torques in task space through the Jacobi transposed to torques that are acting on the dynamics equations of motion. So the tau vector, which goes in here, so instead of equal to 0, we have equal to tau. This is now the sum of all these rotational Jacobian transposed times the external torques. This means we do it for the cart and we do it for the pendulum. And if we sum this up, we're going to get 0 and tau A. Now this was a complex calculation to end up with something which is kind of intuitively clear from the beginning, because this actuator produces a torque which is directly acting in direction of this one generalized coordinate phi. And that's why we have now 0 and tau A. However, this is not generally true. You might have much more complex actuation setups with like linear actuators across multiple joints and whatever. So what you have here is a channel mechanism in order to derive this. And again, what is important, all we need to know for doing this are a couple of Jacobians. Now let's do a slightly more challenging example by adding a spring to the pendulum. Now the spring here is connected at point P to a world fixed point. It has a given zero length and a given stiffness. Now the question is, by adding this additional spring, how does my equations of motion change? Now one way is that we go through Lagrange 2. We calculate the potential energy that the spring produces, and we do this straightforward derivation in order to get like its influence on the dynamics equations of motion. The other way to do so is that you simply consider this spring as a producer of an external force, and that's what we're doing here. This spring produces an action on the pendulum. The reaction is somewhere at the world, so there's no reaction force that we have to apply in our equations of motion. So this action on the pendulum are two forces. There is a force in x direction and a force in y direction, just simply by splitting up these two components. In order to calculate this force, what we need to know is what is the position vector of that end effector. So what is the position of this point? Then we can take the position of this point minus the position of that point, and through this calculate the actual force. So we figure out r of this one point. So this is essentially, I draw this here in blue. So I have my r here, my r. This is this vector. So we go by x and by 2l sine phi in x direction, and I go by minus 2l cosine phi in y direction. That means I can then also calculate the Jacobian for that one point. And now I have my f and I have my Jacobian. So all I need to do is I pre-multiply the f with the Jacobi transposed of that point where it acts on our system. And this is what I get to that. So I have again like a channelized torque acting directly on my equations of motion, which depends on fx and fy, and fx and fy, as indicated here, are just a function of spring stiffnesses and some offsets that we have there. Now this is a very general approach again for an arbitrary force acting somewhere on our system. We have a method in how we transform this into generalized torques that directly influence our equation of motion. And this is what we do in the small quiz that you do for yourself. Very similar to what we've seen before. Now the only difference is we have a new actuator which is now acting our system at the cart. So we're actively moving the cart forth and back. And I want you to figure out, given this motor that produces a force, how does that change the generalized equations of motion?